In this video, we'll be talking about how we find the real zeros of a polynomial. So we saw last time that we can divide polynomials using synthetic division. We learned how that whole process works. And so in this section, we're going to continue to use synthetic division, but for somewhat different purposes here. So to start off, let's look at the example of f of x is equal to negative 2x to the fourth minus x cubed plus 3x squared minus 4x plus 100. And suppose we wanted to find f of negative 3. This would simply be a matter of plugging negative 3 into the function. So we'd have negative 2 times negative 3 to the fourth minus negative 3 cubed plus 3 times negative 3 squared minus 4 times negative 3 and plus 100. So evaluating this, following the order of operations, start with exponents. Negative 3 to the fourth ends up as positive 81. Negative 3 cubed is negative 27. And here we have negative 3 squared, which will become 9. And go ahead and multiply out the negative 4 and negative 3 to get positive 12. And of course, we still have the 100 at the end. So now we have negative 162 plus 27 plus 27 plus 12 plus 100. So here I like to separate the negative terms from the positive ones. So if I add up all my positive values there, I should get a total of 166. So the final answer ends up being 4. So in this case, f of negative 3 is 4. So this hopefully wasn't too bad to do the computation, although it was a little bit time consuming. There is actually a much faster way of arriving at this same answer, and that's where synthetic division will come into play here. The way this will work is I'm going to take the negative 3, the number we had plugged in for x, and that'll go in the box in my synthetic division setup. And then we'll list the coefficients like we usually do. So in this case, we have coefficients of negative 2, negative 1, 3, negative 4, and 100. So going through the synthetic division process like we normally do, as we know, we start by just bringing the first number down, the negative 2. And of course, we'll multiply this number that we have in the box here, the negative 3. Gives us 6, and then adding the numbers in the columns here, we'll have 5. Repeating the process, 5 times negative 3 is negative 15, so we get negative 12 here. So give us positive 36 for the next column. Adding those numbers, we have 32. And 32 times negative 3 is negative 96. And we end up with a remainder of 4. So what I want us to notice here is that what we're getting for f of negative 3 is the same thing as the remainder that we get when we use negative 3 as our synthetic division divisor. And that is not a coincidence. This will happen every single time. This is actually something called the remainder theorem, which allows us to evaluate any polynomial by using synthetic division this way. So let's go ahead and just state the remainder theorem real quick so that we all know what exactly is being said. So this is simply indicating that the value of f of c, assuming that our function here, of course, is a polynomial, equals the remainder when we divide f of x by x minus c. So this is saying exactly what we just observed in the last example, that if I want to evaluate a function at a certain value of x, I could do that simply by doing synthetic division and looking at what the remainder is. What the remainder is equal to is going to be the value of the function at that point. So let's try some other examples like this. Let's take the polynomial function f of x is equal to 2x to the third minus 8x squared minus x plus 5. So in this case, let's find f of 4. So again, what the remainder theorem tells us that we can do is we can take b4, the number we're plugging in for x, put that in the box here, and we list our coefficients like we normally would. So in this case we have 2, -8, -1, and 5. So we go through the ordinary synthetic division process, but really all we're interested in here is what the remainder turns out to be, because that will be the value of f of 4. So again, bring down the 2 here, multiplying by the 4 we'll get 8, adding these numbers we get 0. So 0 times 4 is still 0. Adding this column gives us -1. -1 times 4 is -4. And finally we're left with a remainder of 1. And so what this is telling us at the end here is that f of 4 is equal to 1. The number that I get as the remainder is the value of the function at this particular x value. Let's try just one more example like that. Let's consider the function f of x is equal to x to the 4th minus 4x to the 3rd minus 9x squared plus 16x plus 20. This time let's find f of 2. So again, setting up synthetic division like we've done with the previous examples. We should have this, and then we go through the synthetic division process as always. So start by bringing down the 1, and I'm sure by now we know what to do from here. So in this case, our result is that f of 2 would be equal to 0. Now, there's a couple of things I want us to realize here. First of all, when we're doing the synthetic division, we're getting a remainder of 0, and so that means that the polynomials that we would be dividing here would divide evenly. But this also means, of course, that since f of 2 is equal to 0, that x equals 2 is a 0 of the polynomial. So we talked about zeros in an earlier section, and remember that those correspond to the x-intercepts of the graph of the function. So when the remainder is 0, we can see that x equals c, of course, is a 0 of the function. But also we can see that the quantity x minus c divides evenly into f of x, because we do not have a remainder. Well, this means that the quantity x minus c is a factor of f of x. And that's probably the bigger takeaway here, is that we're getting a factor of the polynomial, which will then allow us to find other factors, which is where we're going with all of this, is to be able to find all of the zeros and all of the factors of any polynomial. Okay, so to observe how all of that works, let's go ahead and consider another example. Let's take the function f of x is equal to x to the 3rd minus 4x squared plus x plus 6. In this case, what we're going to do is we're going to find f of 2, and it's going to turn out that f of 2 will end up being 0. Then what we're going to do is we're going to use that fact in order to factor f of x completely. And from that, we'll be able to find all of the zeros. So let's go ahead and start by doing the synthetic division here to evaluate f of 2. So we bring down the 1 here. and proceed as usual. Okay, and sure enough, as I mentioned at the beginning of the example, we end up with 0 as our remainder. In other words, what we're saying here is that f of 2 is equal to 0. So x equals 2 is one of the zeros of this polynomial. But again, as I stated, this also gives us one of the factors. What we can say now is that the original function f of x, since x equals 2 is a 0, that means that x minus 2 is a factor of this polynomial. The other factor that we're getting here, we can obtain from the coefficients that we got when we did the synthetic division. So I'm talking about the 1, -2, and -3 here. Again, if we think about the synthetic division process and what the result would be, what this tells us is that we would have x squared minus 2x minus 3. So in other words, f of x we can factor as x minus 2 times x squared minus 2x minus 3. So in order to factor this polynomial completely, we simply need to factor what's left, the x squared minus 2x minus 3. And this should be pretty easy to do. We just end up with x minus 3 times x plus 1. So now we have factored f of x completely. And from this, we can indicate what all of the zeros are. So if I want to list all of the zeros of this polynomial, we can see that we have x equals 2, which of course we got by doing synthetic division above. But we can also see that we have x equals 3 and x equals -1. Simply seeing what values of x make the other two factors equal to 0. So these would be all of the zeros of this polynomial function. And so what we're able to conclude from this is that if we're able to find one of the zeros, we can then factor the polynomial, and from that be able to find the remaining zeros. And so this is what we want to be able to do every time, and this is one of the key things that synthetic division will be useful for. So let's try another example, similar to the one we just did. Let's take a look at the function f of x is equal to x to the third minus 7x plus 6. This time, let's find f of -3. Again, it will turn out that this will give us 0. And again, we will factor this polynomial completely. And then we will find all of the zeros of f of x. Okay, so again, find f of -3. We're not going to plug the number directly in. We're going to continue to use our synthetic division process. And notice here that our polynomial is missing an x squared term. So remember that means that we have to account for that term by putting in a 0 as a placeholder. So my coefficients are actually 1, 0, -7, and 6. And we go through the synthetic division process as always. So sure enough, I do end up with 0 as my remainder. So that tells me that f of -3 is equal to 0. So I know that x equals -3 is one of the zeros of this polynomial function. And it also tells us how we're able to factor f of x. What I can see now is that this would factor as x plus 3 times x squared minus 3x plus 2. Again, it would be x plus 3 this time because our x value is equal to -3. So that would be the associated factor there. And so to find the remaining zeros, I simply have to factor what's left. So x squared minus 3x plus 2, we can factor that as x minus 2 times x minus 1. And then we'll go ahead and list all of the zeros of this polynomial function. You can see that we have x equals -3. Of course, that was the first one that we found. But now we also see that we have x equals 2 and x equals 1 as the remaining zeros. Okay, and so our ability to factor a polynomial this way and find these zeros is closely related to what we call the factor theorem. which really just states concepts that we've already observed in the examples we've just been doing. This theorem states that the quantity, x minus c, is a factor of the polynomial f of x if and only if f of c is equal to 0. So when we know we're getting 0 as a remainder, we know that x minus c is a factor, and from there we're able to determine the other factors as well. All right, in the examples that we've looked at, though, so far, you basically have been given one of the zeros. I asked you to find f of 2 or f of negative 3 or something like that. We ended up getting 0 as the remainder, so we knew it was a 0. And then from there, we were able to find all of the zeros. The question, though, becomes, what if I don't have any of these zeros at the outset? Suppose I'm given a polynomial function and I want to find all of its zeros. What do I do in that case? Well, that's where something called the irrational zeros theorem will come into play, which will be the main topic of the next video. So make sure to watch that video and see how we build off of these concepts here in order to be able to factor any polynomial completely and find all of its zeros.